Welcome to this presentation on Z transform. The outline is as follows. We will motivate Z transform as something that simplifies convolution. We will define Z transform, concept of region of convergence. Let's recall the convolution example. We have already seen this. We had two sequences G of n and U of n with only three non-zero entries in each, and then we derived all these values. All other terms that don't appear above are 0. Remember the argument rule. This n over here is equal to the sum of the arguments k and n minus k here. All such combinations should appear here. These are the only non-zero combinations, so you have this. Remember, we need to calculate this expression using this expansion. Because there are only 3 and 3 non-zero entries here, you have a smaller number of entries. In general, you will have to calculate infinite number of terms for every n. So this is what I call as infinite sum, to be evaluated infinite times in general. We will show that polynomial calculation is an equivalent option for convolution. So let us carry out the following multiplication. Remember u0, u1, u2, also g0, g1, g2. So I multiplied by z power minus this argument. Here it is z power 0, so I don't have to write it. Here it's z power minus 1, z power minus 2, similarly here. When I multiply and group the terms, I get the following. The constant term is u0 and g0, I get this. What about coefficient of z power minus 1? That will be u0 g1, u1 g0. These are the only two combinations. What about power of minus 2? Z power minus 2. It will have three terms, 0 and 2, 1 and 1, and 2 and 0. All these combinations add up to 2 here. So sum of the arguments is equal to power of z power minus 1. And this is the same as the argument of y of n in the convolution that we did in the previous page. So you can think of this z as a position marker. As a matter of fact, z power minus I as the position marker, and this is the position marker for the ith instant. So we can say that u0 plus u1 z inverse plus u2 z power minus 2 is another way to represent this sequence. We are going to treat this as a polynomial in z inverse. So the question is, can I get compact form even if there are infinite terms? Here is an example with 3 non-zero terms. So we got only 3 entries summed here. What if there are infinite number of terms in this u? Then we will have a polynomial in z power minus 1 with infinite number of terms. We will show that it is possible to express that sum in a compact form under some conditions. But before that, we will motivate why we want to do this. So convolution is polynomial calculation. This is convolution. Recall the argument rule. As I mentioned earlier, convolution is cumbersome. It has infinite addition, and you have to do this infinite times. We showed that polynomial calculation also gives identical results. We checked it by comparing the coefficients of constant term, power of z power minus 1, and so on. The beauty of this is that the polynomial approach requires just one multiplication. The moment we are able to express this as a compact expression, this also as another compact expression, all that we need to do is one multiplication. We don't have to do this infinite additions infinite number of times. The only thing we have to be careful about is this sum, which might have infinite number of terms, is to be evaluated carefully as there are infinite terms. We will denote this as u convolved with g of n has the polynomial representation uz gz. Remember, this is nothing but this expression. Remember, we use this simplified expression with asterisks to denote this, and this uz gz is what we have. So, we would later on call this a pair, but remember this is something that you will have to use this again. You may even want to write this down. So, the reason why we introduce this polynomial notation is to simplify this convolution, which can be replaced by a simple multiplication. Okay, as I said, motivation. Let us consider the LTI system with impulse response g of n. So, we have the time invariant system, linear time invariant system, which is initially at rest, is excited by an input u of n, you get the output y of n, and we derived the following relationship. Recall the lectures given earlier, we got this general expression. In fact, we said that because of this impulse response g has all information about the system, and comparing term by term, we can get the expression for one term. Remember, the moment I put braces, I mean the whole sequence, and this one is just one of the terms in that, namely the one evaluated at time instant n. So, here is the expression we have. What we want is the following. In the place of un, I put uz, in the place of yn, I put y of z. How do we do this? We replace this with the polynomial with the components of y of n or the elements of y of n multiplying appropriate power of z inverse. Okay. Similarly, you get u of z. So, you have u of z and y of z, and so do we get y of z equals uz gz. In fact, we showed in the previous slide, one of the previous slides, that we can replace this convolution with this multiplication. So, this is the motivation, and where is it useful? It is useful in our LTI systems, which we will study in this course on control system design. We will show that this representation will simplify calculations immensely. So, let us define Z transform. Z transform of a sequence u of n denoted by u of z is defined as follows, where z is such that there is absolute convergence. Remember, there are infinite number of terms. We have to make sure that it makes sense to even write this expression. There are infinite number of terms, under what conditions this will converge. So, what we will do is we will choose z such that there is absolute convergence. What is absolute convergence? It means not that this sum is bounded, but this sum which has every element represented in absolute form is bounded. All z that satisfy this condition is said to belong to the region of convergence. Okay. Why do we need absolute convergence? Why do we not just say this sum to be bounded? Why do we want this sum to be bounded? So, we will see that in the next slide. We will also see the benefits of Z transform shortly. Okay. This is how we defined u of z, where z is so chosen that there is absolute convergence. As I mentioned earlier, there are infinite number of terms. We have to make sure that the sum converges. The stronger condition of absolute convergence allows complex quantities in u and z. Remember, this is a stronger condition because if this is satisfied, this is automatically satisfied, namely this is also bounded, because here there could be cancellation of some terms. Here there is no cancellation of terms because you have everything with only magnitude considered. So, absolute convergence restricts ROC, the region of convergence, to one side of a circle. So, we will see this shortly. This ensures uniqueness. In the textbook, we have given an uniqueness example. I strongly suggest that you read the textbook and see that example. Now we will define what is meant by a transfer function. Recall our LTI system, linear time invariant system, with input un and the corresponding output yn. The impulse response is denoted by g of n. Let us take its z transform, let us call it g of z, capital G of z. Capital G of z is known as the transfer function. In fact, in this course we will use this capital G of z as the transfer function. Let us take an example of z transform. Find the z transform of this impulse response, which is given by a power n into 1 of n. A is general, it could be real, it could be positive, negative, it could even be an imaginary term. By definition, recall the definition of Z transform. It is A is an A power n into Z power minus n, n going from minus infinity to plus infinity. But why are we starting at n equals 0? It is because we have 1 of n. So all the terms with negative n will be made 0 because of this 1 of n. So I can group it like this, and then I expect this absolute value to be less than 1. If that is so, then the sum exists, and I can write it down using a well known formula. It is a sum of geometric progression. So you can immediately write this as 1 over 1 minus this ratio A Z inverse, which can be simplified as Z over Z minus A. But remember, we have to make sure that this inequality is satisfied. But before that, notice that Gz is in general a ratio of polynomials nz by dz. We started with a very simple expression, a power n into 1 of n, but the moment you add them over this index going from 0 to infinity, it becomes a ratio. So in general, this G, namely the transfer function or Z transform of almost any sequence, will turn out to be a ratio of polynomials in case or whenever you have infinite number of terms. You have to remember this. So I would like to add a small note on our definition of Z transform. Our Z transform is known as the two-sided Z transform because this index goes from minus infinity to plus infinity. Most control books, however, use one-sided Z transform. That is because they only use causal signals, that is u of n for n greater than 0, but we use two-sided Z transform. Because of this, our results could be slightly different from those in standard textbooks. We will make sure, however, that our results are consistent with our definition. Why do we use two-sided sequences in this course? Because these are useful in some topics such as identification covered in the textbook. What are the benefits of Z transform? The first thing is convolution calculations can be carried out easily. Of course, there is a burden of converting polynomials to closed form expressions. We also need to invert Z transforms back to time domain. This requires additional effort, but we will show that it is possible to develop techniques to simplify these operations. Overall, Z transforms help simplify calculations. Z transform is suitable for studying stability, causality and oscillatory behavior. In addition to these benefits will come handy while designing controllers. With this, we come to the end of this presentation. Thanks for joining. Goodbye.